Hey folks, two other things I want to show you about multiple linear regression here, and that should complete our tour of multiple linear regression for this week. But as you've been getting into multiple linear regression, I hope some interesting things have been coming to mind, and so I want to test your brains a little bit and show you some implications of multiple linear regression. So let's say that I start with a multiple linear regression model. Let's say I start with a simple linear regression model of price and square feet, like we've always seen a lot lately. So just my usual simple linear regression. And let's say that I get a predicted model with some predicted intercept coefficient and slope coefficient. So I got my theoretical model and my estimated model. And as you've seen before, if I want to actually show what the linear regression line looks like, I've been able to do that pretty easily. Because I can put my response variable on my y-axis, I can put my explanatory variable on my x-axis, and then I can plug in different values for square feet based on my data, and I can get a linear regression line. So that's how we thought about this before in the simple linear regression case. But what happens if I change this to a multiple linear regression situation? So let me clear away this. Let me clear away this. And let me change my model. Let's say we add in age of my house. So now I have a multiple regression model where I am predicting the price of a house simultaneously with square feet and with age. So how do I show the regression line? Because before I would just put my one explanatory variable here and then have my response variable over here. The moment you move to multiple linear regression, it becomes much more difficult and in many cases impossible to actually show a regression line to represent your whole model. And the reason is this. Great, let me put square feet on here. But in order to get my observations, I need a square feet and I need an age. How do I fit square feet and age on here? Well, in reality, the way this works, and this is why I'm not going to have you plot regression lines ever because it quickly breaks down. Each explanatory variable is one new spatial dimension. So you can think of age as being another axis that's, say, coming out of the board. And instead of getting a regression line with square feet and price, what I actually get is, well, what do a bunch of lines add up to? They add up to a plane. And so, for example, instead of just having a regression line with square feet and price, I'm just going to write age down here. say 3D axis. If I were to actually try to plot what my model looks like, I need an input for square feet, I need an input for age, and I can do that a bunch of times, and it actually basically becomes a sheet of paper sticking out of the board. This is just the case with two explanatory variables. It suddenly becomes a plane, a sheet of paper, not just a line anymore, because again, I need to predict for one variable and I need to predict with another variable. So I need to use two different values, and that's no longer a line. That gives me this three-dimensional object. There's nothing to show you after that because let's say I added in another variable. Do this down here. Say I added in beta 0, beta 1. Let's keep this like before. Square feet plus beta 2 age plus beta 3. We'll just say number of bedrooms plus air. For every new explanatory variable I add, I have to, my predicted thing adds another spatial dimension. And this is where we get to more of the stat theory and it just gets very goofy. You need to predict with a four-dimensional object. So my regression predictions are a four-dimensional object. For every single explanatory variable I add another physical dimension to what my predictions look like, if I want to show them all at once. So we don't do that because it's physically impossible to do that. Instead, what we can do is we can hold one of these two things constant. So for example, I can show the relationship between square feet and price. Let's do this here. Let's pretend we're just doing square feet and age, and I'm using that to predict price. I can show the relationship between square feet and price at different levels of age. So I can say age equal to 10. Gives me one line. Age equal to 20 gives me another line. Age equal to 30 gives me another line. So all I'm doing is saying, give me fixed age at some value, 10, 20, 30, and then graph the relationship between square feet and price. In a sense, I have an infinite number of regression lines because I can set age to an infinite number of values. I'm not going to have you do this. I know I say that a lot, but because I want to ease anyone's tension of, oh my gosh, this is getting really crazy, this is getting really mathy. I'm just trying to illustrate why we can't do one simple line anymore. We can't do one simple line anymore because I have to plug in for two variables at once. And I can do this the other way. Instead, I can look at the relationship between age and price, and I can do it at different levels of square feet. And so I can say that this is square feet equal to 100,000, or square feet equal to 150,000, or square feet equal to 200,000, etc. And I can just keep going. So I can put in a value for square feet and then just change age and look at the relationship between age and price. So that's what's going on with multiple linear regression. The implication is that for our assumptions, when I have you look at the initial assumptions about the relationship between your explanatory variables and your response variables, remember I was having you look at the scatter plot of each one. Something like this. So now when we check assumptions with multiple linear regression, now you just need to do it for every single variable. And we'll just make it a little bit different here. Everything else about our assumptions is exactly the same. It runs the same, there's no issue there. But when we're checking the relationship, the initial view of our scatter plot, we just need to do one for each variable, one for each explanatory variable. And that's all there is to it. And the other big change then is, how do we interpret our slope coefficients? Everything is exactly the same. So a 1 unit change in square feet is associated with a beta hat, so 1 unit change, excuse me, just a beta 1 change in price. On average, the main thing we need to add in now is that we have to say holding all else constant. Because there may be a relationship between square feet and age. And so what may happen is that if I change square feet, that may be related to a change in age. And if I'm changing square feet and age at the same time, well, I'm no longer just talking about beta 1. So if I want to interpret beta 1, the relationship between square feet and price, completely on its own, I have to say hold age constant, because a different age gives me a potentially different relationship between square feet and price. So I have to say holding age constant. And this will never change. You just add on holding all constant when we interpret our slope coefficients. And everything goes from there. So I will take off points if holding all constant is not used, because it completely changes the meaning if you don't say holding all else constant. If I try to interpret this as a beta 1 unit change in price, on average for every square feet change, then that implies that, well, age might be changing too. And then that would affect what beta 1 is. So that's why I have to say holding all else constant. These things might be related. We're predicting price using square feet and age at the same time. So if I want to interpret these things, I have to say holding all else constant. Awesome. Okay, last concept. And I want to revisit our big circle of sums of squares total. Remember, variation in response variable. So if I think again as this circle as my sums of squares total, my total variation, say in price of a house, you remember that I've diced this circle up by saying my model or my explanatory variable, in this case, let's call it square feet, was eating up a chunk of that variation. And that chunk of variation we're calling sums of squares model. And the rest that had not been explained was the sums of squares error. And I had defined that as my r squared. So this was the simple linear regression case. So what happens when I add in another explanatory variable? Many different things can happen. And you will get this as a challenge sheet next week. But let me show you one possible thing that happens. But probably you'll see what is probably the typical thing that happens. When I add in another explanatory variable, I get another chunk taken out of my sums of squares total. And now, my sums of squares model is this whole thing. And I'm just going to draw a little. So now my sums of squares model is this whole thing. And my sums of squares error is still what's left over. So the more variables you add, basically, the more circles you just start to add in here, and they may overlap in different ways. But that's the idea with multiple linear regression. There's one other interesting thing that you may have noticed, is that in addition to the new explanatory variable taking out and explaining more of my response variable, and why don't I label this thing as age? That's not clear. In addition to age taking out some of this variation in price, there's this region here where age and square feet overlap. This is represented by the sort of relationship between age and square feet. So you can think of this as that square feet is related to age. They overlap somewhat. And we'll get to this idea in future weeks with multicollinearity. But this area here, up top, is the area that's just explained by square feet. This little area down here is just the area explained by age. And then this area here, where age and square feet overlap, and they overlap the big circle of price, is what's age and square feet both explain together and explain the same thing. They explain this variation redundantly. because they're overlapping on it. So they're both explaining the same thing. And I'll revisit this in future weeks, but when R calculates significance, so R calculates significance, and I don't mean the adjusted R squared, the R software. R software calculates significance as the, if you want to think of it this way, the amount of unique variation explained by a variable. So it excludes the overlap for all of it. So when our software package is calculating, is square feet significant, is age significant, it's taking out the region that they overlap because R doesn't know what to do with it. Does it go to age? Does it go to square feet? Where should this overlap go? It doesn't know what to do, so it X's it out. Kind of like this. So R gets rid of that and says, great, the significance of square feet is just going to be this overlapping chunk here of just square feet and price. The significance of age is just going to be this overlapped region here, just age predicting price. This non-overlapping region, age with price. The overlap between age and square feet, this little triangle, it does not use when calculating the significance of age in square feet. When doing the sums of squares model, it absolutely takes this whole thing. So the sums of squares model is still this whole thing, but it just does not include this overlap in explanatory variables in either one of them. So that's a more advanced concept. We'll get to that in the future, but I just wanted to prime your brain a little bit for what's happening with multiple regression and give you some more advanced ideas to work with. You will see as you go through the activity that you don't need to worry about in as much depth as this yet. I'll challenge you on that in future weeks. And I guess the last thing to put in here is that you've seen in the R output that there's this thing called adjusted R squared. And what adjusted R squared does, it's interpreted the same way as the R squared, but what it does is it penalizes you for adding in explanatory variables that don't do much for you. Because as you can probably imagine, you can throw in a lot of variables in here and just start to eat up this circle with explanation. But they may not actually be statistically significant. You just are artificially adding variables to make your significance look bigger. So the adjusted R squared takes that into account, and it decreases your R squared depending on whether or not the variables you've added are significant. And you can look up the formula, but one way that it's written is 1 minus the mean square error divided by the mean square total, which you can get from the ANOVA table we looked at in the other video. There are mathematical ways to connect these things. Not worried about that for this class. But just the idea that, yeah, I can still say that the model explains some percentage of the total variation in price in my response variable. But then what I can do is I can say that that percentage of variation that's being explained, I am taking into account whether or not my variables are significant. If my variables aren't significant, then in the adjusted R squared, I am penalizing myself for adding in insignificant explanatory variables just to increase my R squared. Great. So that's a lot of stuff. And definitely ask me questions. Go back through this. Feel free to read the book. I'll write some of this stuff up in written form. Like I'll make a nice little graphic for this, and definitely reference that and use it for your own learning and knowledge. But I just want to give you this groundwork as you think through doing these activities and as you answer these questions. So that's it for multiple regression this week. Check out all the other resources, and thank you much. Have a nice week.